This video is about limits. We encountered limits in class on Monday when we were trying to think about how to define the instantaneous velocity of a cat or a worm or whatever. And in this video, we'll step back and look at limits on their own without this other idea of instantaneous velocity. So let me first state the definition of a limit. So we say that the limit of f of x, the limit as x approaches c of f of x of L, what does that mean? Well, that means that f of x gets closer and closer to L as x gets closer and closer to c. So we vary our x in here. We sneak up on c. We get closer and closer and closer to c. And then we look to see if the function, the value of the function, gets closer and closer and closer to something else. And if it does get closer and closer to something else, that something else it gets closer and closer to, we call L, the limit. So this is sort of a weird idea, but I think once you do a few examples and just play with some numbers, you'll see how this all works. So I'm going to do 3 examples in this video. The first one is almost silly, but I think it's good to start with. And that example is this. So we want to know the limit as x approaches 3 of f of x, and f of x is just going to be the cubing function, x cubed. So one approach to this, we could imagine filling out a table. So we're just going to use a calculator and plug in some numbers. So what if x is 3.1? 3.1, and I cube that, and I get 29.79. All right. What about 3.01? What happens if I cube that? I get 27.27. What about 3.001? What if I cube that? 27.027. Let's do one more. 3.0001 cubed equals 27.0027. So it sure looks like the function f of x is getting closer and closer to 27 as x gets closer and closer to 3. To be super sure, we could check from the other side. So what if x approaches 3 from below, 2.9, 2.99, and so on? Well, again, let's just plug into our calculators. 24.39, 2.99 cubed, 26.73, 2.999 cubed, 26.973, and one more, 2.9999 y to the x3 is 26.9973. So here are the results of our experiment. And I would say that the limit as x approaches 3 of the function x cubed is 27. Why do I say that? Because as x gets closer and closer and closer to 3, but not actually hitting 3, closer and closer and closer, f of x gets closer and closer and closer to 27. See it over here too. As x gets closer and closer and closer to 3, f of x gets closer and closer and closer to 27. Now for this limit, you could just plug in x equals 3, but most of the time when we're dealing with limits, it's some sneaky situation where you'll get in trouble if you actually plug in the number. So you have to sneak up on it. So we'll do 2 examples next, which will be a little more interesting than this, and ones where you can't just plug in the number and see the limit right away. Here's the next example. Suppose we want to know the limit as x approaches 0 of sine x over x. As I let x get closer and closer to 0, does sine x over x get closer and closer and closer to something? Well, let's see. Let's do what we did before. Let's fill out a table of numbers. Now we're going to let x get closer and closer to 0, but not actually hit 0. And when you're doing this, it's important that your calculator is in radians and not degrees. All right, let's try it. So x is 0.1. I'm going to do sine of 0.1 divided by 0.1, and I get 0.998. 0.998. Let's do another one. Sine of 0.01 divided by 0.01, 0.99998. Well, you can kind of see where this is headed. Let's do one more. 0.001, 0.001, sine that divided by 0.001, and a lot of nines. 0.9999998. So it sure seems to me that this is getting closer and closer to 1. So I would write this as the limit as x approaches 0 of sine x over x equals 1. Why do I say that? Because as x gets closer and closer and closer to 0, f of x is getting closer and closer and closer to 1. And note, by the way, that you can't just plug in x equals 0 to this function, sine x over x, because you're dividing by 0, and your calculator will refuse you if you try that. So sine of 0 is 0, that's fine, but if you take 0 and divide it by 0 while you're dividing by 0, your calculator will tell you that's an error, so you're out of luck. So the limit is 1, and let me just show a view of this graphically. So here's our friend Wolfram alpha, and I asked it to plot sine x over x from -2 to 2. And so you can see as x gets closer and closer and closer to 0, from either direction, the function, that's this line here, gets closer and closer to 1. At exactly 0, this function isn't defined, so it's kind of got a little hole in it. But you can get as close as you want to that hole, and you'll get as close as you want to 1. Let's do one more example. So here we're interested in the limit as x approaches to 0 of sine 1 over x. It's just a little different from before. Last time we had sine x over x. This is sine 1 over x. We want to know, as x gets closer and closer to 0, what does sine 1 over x get closer and closer and closer to? If you want, you might want to take a moment and try this on a calculator on your own before I show you the results. All right. So here we go. Again, make sure your calculator is in radians. And I'll just plug in and we'll see. So I've got 0.1. I need to turn that upside down. I hit the 1 over x key. And then I'm going to sine that. And I get minus 0.544. Okay. Let's do the next one. 0.01. Turn that upside down. Take a sine, I get minus 0.506. So maybe it's going to 0.5. Let's see. 0.001. I'm going to just plug in that number into the function. 1 over x. Sine that. 0.827. It's weird. Let's try one more. 0.0001. Upside down, sine it. Minus 0.306. And it's hard to see where this is headed. Let's do one more. 0.0001. Upside down, sine. 0.0357. So at this point, we're faced with a little bit of a puzzle. Based on this experiment, I would conclude that actually as x gets closer and closer to 0, sine 1 over x isn't getting closer and closer to anything. It seems like it's wiggling around more and more. So I would state that conclusion by saying that this limit does not exist. So the limit as x goes to 0 of sine 1 over x does not exist. This does not get closer and closer to anything. It keeps wiggling as x approaches 0. So that's a little bit of a surprise, but it's good to know that not all limits exist. And let's look at a picture of this. So here's Wolfram alpha, and I'm plotting sine of 1 over x, again from -2 to 2. And we can see that what happens is sine functions are wiggly functions, and as we get closer and closer to 0, they wiggle faster and faster and faster, and faster and faster and faster. And so as we sneak up on 0, the wiggles just keep getting faster. The wiggles don't slow down. Another way to think of it, more in terms of just telling a story about what this function does, is 1 over x, a plot of 1 over x, that function explodes near the origin. This is 1 over x. It's 1 over x. And so the function, right, so the first function that happens is 1 over x, and that goes very, very fast, increases very, very quickly as you get close to 0. So this is a sine wave whose period is increasing very, very, very quickly over tiny, tiny little intervals as you get close to 0. In any event, you can think about it in terms of this graph, in terms of what 1 over x does, compound functions. You can just think of it in terms of this table of numbers. The bottom line is this limit does not exist because this column of numbers is not getting closer and closer to any constant.